Hey everybody, welcome back to Physics with Dr. T. In this week's laboratory, we're going to be exploring the electric charges and the fields that they produce. Now, we've all produced electric charges from time to time, usually zapping our door or watching lightning. And by the way, let me recommend you take a look at the lightning video that I have up on D2L. But in this laboratory, we're going to be exploring those two charges and the fields. You'll be mapping out the fields, demonstrating that they have the configuration that we believe that they do. And then at the end of this lab activity, you're going to demonstrate that the electric charge produces a field that's of a significantly different magnitude than the field produced by a gravitational charge, aka mass. But before we get into the science of all of that, let's take a look at this week's pre-lab activity. Okay, so in this week's pre-lab activity, what we're looking for is to just generate some charge on your own. Now, it's kind of familiar thing because we've all zapped our hands on the thing, probably coming off of a trampoline or rubbing, just in wintertime. Here, the South Dakota winters are just, dry. And so you're going to generate charge, just have a lot more electric discharge. I know for sure I have zapped my cat many, many times, just petting the guy, just petting him. Zzz, zzz. So what we want you to do is to demonstrate charge buildup. You can put socks on your feet, make sure they're dry, clean socks, and then you rub your feet across the floor and see if you can discharge at like a door or some other metal surface. If you've tried that multiple times and it just doesn't work, that's going to happen sometimes, you can look at some alternate. If you have access to long hair, maybe you have long hair or you know someone who does and you get their permission to do so, let's get a comb and run it through their hair a few times, several times in the same direction, the same steady pattern. If their hair is clean and dry, you should start to accumulate charges and be able to demonstrate that their hair is starting to get a little charged. Finally, if that doesn't work, you can rub some kind of rubber against wool. It doesn't necessarily have to be rubber, though. It could be thin plastic. For example, a Walmart bag or Hy-Vee bag or some other single-use bag can also accumulate charge pretty easy if you rub it against a fleece blanket, like these nice, fluffy, warm blankets that are in wintertime, really nice. So, but then you just discuss what you've explored. Now for this part, you don't really need any photo evidence or anything like that. You just be ready to talk about what experience was. But for the second part of this pre-lab, you do need to take a few minutes on the simulator that's on the PhET simulator and create a configuration of charges that's very similar to what's going on in the lab. You'll put a bunch of blue negative charges in a line and then a set of red charges, positive charges in a D shape, similar to, again, the map that you see in your D2L setup. The idea here is for you to see some simulations that you're going to be mapping out in the classroom. Now, the simulator doesn't show equipotential lines. It shows gradients of color. So the more intense the field, the deeper the color is of red or blue for the field. But hopefully, in setting up these charges, you kind of get a better sense of what you're going to be walking into in the lab. And that hopefully will bring you a little bit better understanding of the actual charges that are set up at your lab station as you're mapping your electric fields. Once you've got your map worked out, simply put that into a Microsoft Word and answer the question that you see in the pre-lab. You really want to kind of talk about the charge that you built up and whether or not you found it easy to charge up or not discharged, but definitely pay attention to the fact that you did create a lot of charge. And once again, take a look at the lightning video that's on D2L if you have a chance. It's pretty cool. And that's it. Go ahead and have that ready to be submitted, and let's go talk about the theory. Okay, to really get what you're wanting to get out of this lab activity, which is a better understanding of electric charges and electric fields, let's take a few moments and look at the theory that underlies what's going on here. So, for example, we have here Coulomb's law. This is a law that was developed in 1789 on the desktop by a man named Charles Coulomb. So what we have here is Coulomb's constant. This is some number. It basically represents how space responds to the presence of an electric charge. And then in this we have two electric charges. They're going to talk to each other somehow through the electric force. And then they have to be some distance apart for each other. The closer they are, the more powerful the force. The farther away they are, the less powerful the force. And so that puts the r squared on the bottom. And we refer to this again as Coulomb's law. Now, if this looks a little bit familiar to you, and maybe you've been looking down, but if this looks a little bit familiar to you, that's because it looks very similar to another equation you were working on once upon a time. This is referred to as the universal law of gravitation, or the law of universal gravitation. I always get the universal location wrong. Anyways, here we have the gravitational constant. It's kind of how space responds to the presence of a mass being there and having gravitational pull and effects on other masses. And then we have a mass, these two masses that talk to each other. Now, we used to call them masses, but now we can kind of call them mass charges or gravity charges, and these are electric charges. But it doesn't change what you understand about gravity. So let's lean a little bit on, because these are very similar, let's lean a little bit on this similarity. We can only go so far, though, and I'll explain why in a moment. But here's the distance between those two. So what we talked about in gravity, in a lot of ways, will apply here, but only for electric charges. Now, the reason that I say that there are some limitations that we can go with, we compare electric fields with gravitational fields, is because with electric fields and electric charges, we can do all kinds of configurations and make use of these in a desktop kind of way, and even smaller. Gravity, on the other hand, it doesn't quite work so well. We don't have weird shaped planets and bodies out there that are massive because the gravitational forces collapse them all and crumble them back into spherical shape. So this never happens, but you definitely have ability to do this without losing integrity of the instrument that you're working with. And we can talk about more of that one-on-one in lab. Now, another concept that is going to be useful for you to understand is a concept called equipotentials. This is a little bit early for this concept to really make perfect sense, but the general idea is, if you think about, again, let's use the gravity analogy. We take a ball, for example. If I'm going to drop this ball, and I drop it from different locations that are the same height that it's going to fall, it's going to have the same amount of energy available to the fall. And so we can think of this surface in a certain area about the Earth that has the same potential energy for a given mass in the gravitational field. Now, if I take this ball away and I imagine this field, this surface here, has anything changed? Nothing's changed. Gravity's still going to be right there. We just don't have anything to drop and fall in there. So we don't really have a gravity potential like we have for electricity. But because we can work with electricity with a much smaller scale, then this concept of an electric potential becomes much more useful, because we can have an electric field without electric charges being in that field to start zipping along because of the presence of the electric field. So here is an example of your map that you'll be drawing in this lab. And what you'll do is you'll use something called a digital multimeter, which is just a tool that has different meters built into it. And one of those meters is going to be the voltmeter. And in today's lab, all you need to know is that we're going to measure a voltage, just like your cell phone charger. If you look on it, it has a voltage output like 2.0 volts or so 5.0 volts or 9.0 volts. It's not a very high number. Even though coming from the wall, it's usually like 60 volts. It's a pretty big number. And most other electronics also have some kind of voltage there. And you probably have heard about the word voltage. And you're going to be using this idea to measure these points on this field map that you have. So you put one probe, your negative probe, the black probe, also called the COM, right here at this negative terminal. And then you'll take the positive probe and you'll just move it around the surface gently, because you don't want to tear the paper. But you'll move it around the paper and find locations of a specific value. You'll notice I've given you some examples here that they're really close to about 2 volts. You're going to do that 2, 4, 6, 8 volts. When you find that point, you'll mark the similar point on your paper, and you want to be careful. These papers are gridded, but that doesn't mean you have to stick to where the pluses are. That's kind of like graph paper. You wouldn't change your drawing just because the graph paper line is really close. Make sure that you're careful about drawing this as accurately as you can relative to these nearby positive, these what look like plus signs, but they're actually grid lines. And you get as close to this value within reason. You don't have to spend 5 minutes trying to find this point, and there's going to be some jumpiness. These papers are old. And once you've mapped out these several points, about 5 to 6 points will probably do good across the entire page. Then you can connect those dots into a surface, and this becomes a surface of equal potentials. That becomes a reference point for you to be able to draw your electric field lines. That's what we're really looking for right now. And you connect those dots, and then what you'll do is when it's time to go back and draw them, and you want to draw them in a slightly different color, if you could use a different color, or if you map your equipotentials in pencil and your field lines in pen, something along those lines that would give you some really good visual dynamic activity. And then the rules, which are listed in your lab manual, will state that your field line comes out of the surface, right at the surface. Electric charges sit right on the surface of conductors, so make sure your lines don't go inside the conductor. They come out at right angles, but they also cross equipotentials at right angles. So we have to make sure that you bend it so that it can cross at that nearby point on the equipotential at a right angle. And you continue it on, make sure that you cross all your equipotentials at right angles, and then let your field line land at your charged surface at a right angle. Put your arrow in place, pointing the direction from positive to negative, and then you do this for several field lines to kind of give a good sense of what's going on between these two charged surfaces. Once again, this idea of equipotential surfaces is a little bit fast, so mostly we want to just kind of pay attention to the fact that we're just using it as a means to an end. We're trying to get those electric fields, and the concept of electropotentials that will come a little further along. So, if you have any questions about if there's any way that we can help that concept land a little bit better, let us know. For the first part of this lab activity, you're going to be mapping out the electric fields, and to do that, you're going to start out with this. I'm going to start out with this conductive paper that has a gridded conductive surface and conductor paint that has been laid out in a particular configuration. You will have this set up on a cork board that you will fix this onto using conducting thumbtacks and a couple of clips. And you simply push this into place. Make sure that they're in good contact. Do it with both. Make sure that your negative contact is over here, and don't let this come over to the surface too much. Now in this configuration, you can have your ports coming in from your 850 universal interface, and then you can connect your probes to it as necessary. In order to make measurements of this, you'll be using this digital multimeter. We'll be using it as a voltmeter. In order to do this, you want to turn this to the V that has a straight line with dashed lines underneath it. This represents direct current or DC circuits. If we were doing something with AC circuits like sinusoidal waves, we would be using the alternative, but we're using this one in this case. In order to make this work, you want to take an alligator clip and connect it to your Coulomb probe, and then connect this to your surface. Now, this is not powered up, so this is not going to demonstrate anything live, but once you've got this in place, then you gently move your probe around the surface, and you will see some changes on your digital multimeter in the volt setup. You are going to look for different positions that are around 2 volts, 4 volts, 6 volts, 8 volts, and you'll confirm that the voltage inside this region here is fairly constant. These are spaces in your worksheet that you can fill in as you're going along and keep track of, so you don't have to write anything on your page other than the dots corresponding to the particular voltages. Once you have mapped out all the dots that you need for your equipotentials, this part is basically done. Anything else after this can be done offline. You can go and proceed with the next part, or you can take a few minutes and begin making your equipotential lines and connecting your field lines from surface to surface. Please make sure that when you have finished the lab activity for this part, you turn off your digital multimeter and you store all the components back inside of the box, which can be removed and separated as such. While you're performing part 1, you'll want to have 2 BNC cables connected into port 1 on your 850 universal interface. So you'll have the black going into the common or the ground port, and you'll have a red one going into the active power source. You'll set up according to the instructions in your lab manual, and then you'll join these BNC cables to the connectors that you've already placed on the conductive paper. For the second part, you're going to be exploring the electric charges that you accumulate onto a few different items. And to do that, you're going to use this item, which is referred to as an ice pail, only because of when it was first used by Mr. Faraday back in the 19th century. He was actually using an ice pail, but in the years since, we've come to figure that a mesh is a more superior surface to use for this type of experiment. But you can see that there are 2 surfaces. One is the interior surface, the other is the exterior surface. They are not connected, so this creates a field protection envelope around a sensor envelope. To connect the setup, you're going to use your passport charge sensor, and you'll use these two clips. You put the positive on the inside and the negative on the exterior, and then you'll mount this on the 850. To mount your charge sensor onto the 850, you simply put it into a port, slide into place, make sure that it locks into position, and then you hit 0 to zero out your charges. And you want to zero out anytime you start getting problematic charges on your setup. Before you actually make any measurements specifically with the charge pail and the charge sensor, you're going to want to make explore some of the charges that you can do. Now, before you do any kind of rubbing of materials together, your first step is to figure out what the charge is on these before you actually do anything else. So you'll simply dip this inside of the interior bucket. Make sure you don't let it touch the sides or the bottom so that it discharges and transfers charge to your sensor. And what you'll do is you'll just give it one rub and see if you've added any charge to it, sit inside the pail. Then you'll do a few rubs, see if you put it inside the pail, if it's accumulated charge. And finally, multiple times, just an endless number until you see if, and then dunk it inside of the pail and see if there's any charge. You'll be able to look at these charges by looking at the Pasco graph setup as you're going along. You'll try different objects in combination, but the key ones that you want to look at are the ones that are going to give you the best charge. Sometimes you're going to see some fluctuations in how much charge is actually accumulated on there, and the reason for that is because of whether or not you're moving charge back and forth between the rubbing object and the rubbed object. So there's some play in there that you want to explore a little bit before you take your final data on these. The final part of this lab activity is for you to demonstrate and see how strong the electric field is compared to gravity. In order to do that, you'll be supplied with what's called a pith ball, which is just simply a little styrofoam ball suspended from a very thin, light string and coated with a chargeable surface. In this case, these are coated with graphite, which is reasonably conductive on the surface. Your TA has this available and will come around when you're ready to make this measurement. You will charge it with one of your rods. It doesn't matter which one. Just make sure that you do the charge. And then transfer the charge to this and demonstrate to yourself that there has been charge transferred. The question you want to ask yourself, how can you be sure? And then once you've confirmed to your mind that there's been charge transferred, you dunk it into the charge pail and use your Pasco reading to get an average for several seconds of how much charge is on there. And then you can use that information to compute how much electrons you actually transferred onto here or transferred away, depending on the charge, and follow the steps to determine which field is stronger, the gravitational field or the electric field. And that does it for this week's walkthrough. If you have any questions, make sure that you talk to your TA, that you ask me any questions, your TA any questions, your lab partners any questions. We want to make sure that you have this understanding. Don't forget to take advantage of the Physics Help Center. Even if you have a good understanding of what you're doing, being able to do your homework around other people who are doing a similar type of homework can be very advantageous. So until next time, let's see you in the lab. That was an okay run through, so we're going to try again. Kind of have it in our head. Does it look like it? No? Okay. Looks like it on that camera. I don't know what it looks like to you guys. And shit.